Welcome back, students. Up to this point in class, we have contented ourselves with ideal gases. We have made a few forays into other substances, namely when we use the total differentials for state functions rather than invoking the ideal gas law. In this chapter, we will look into real gases. We will discuss how real gases behave and when and why they deviate from the ideal. So the learning goals for today are going to be to, like I said, describe why gases deviate from ideal. And these typically happen at high pressures and low temperatures. We'll then look at a couple of real gas equations. The main ones that we'll use are the van der Waals equation, and we'll also talk about the Redlich-Kwong equation. Those are pretty similar. We'll mention a few others, but we're not going to go into them in too much detail. We're going to figure out where these laws come from and explain why they only offer qualitative agreement with their experiments. And then we'll look at an important law, the law of corresponding states, which is an attempt to describe real gases without resorting to gas-specific parameters. And lastly, we'll look at the fugacity, which is a term that a gas chemist needs to do in order to actually accurately calculate equilibrium for gas phase reactions. The ideal gas law, which we know as PV equals nRT, was originally formulated based on experimental observation of the behavior of a variety of gases. It turns out that most gases under typical pressures and temperatures behave ideally, hence the formulation of this ideal gas law. This is because molecules in the gas phase are very distant from each other relative to their own molecular or atomic size, so they can be thought of as non-interacting particles with point masses, since they're in general very small. When these assumptions hold, gases behave ideally. So you can see this curve here at 426 Kelvin for a particular gas. The ideal gas law does a pretty good job in red at describing the experimental data in black. As we get to low temperatures, though, that begins to not be the case. So in blue and purple are a couple of our real gas equations, and you can see that the blue one does a pretty good job, while the purple is, okay. And the ideal gas law totally breaks down at 310 Kelvin. Now, before you get too worried here about the ideal gas law not applying at 310 Kelvin, which is a normal temperature, note the molar volume here is not very normal. So the ideal gas law is breaking down at molar volumes of 0.5 liters per mole. In general, right, you can also see the pressure here is 400 bar, right? So in general, the molar volume for a gas at 310 Kelvin would be like 24 liters per mole. So for a half a liter per mole, we're under some pretty extreme circumstances. And that's when the ideal gas law breaks down. Nevertheless, it's kind of surprising that if we heat up the temperature, we get a better prediction. So what's going on here? Well, what's going on is essentially under high pressures and also under low temperatures, it turns out that the gas phase is not the most stable state of matter. So as you compress a gas or as you cool a gas, at some point that gas will tend to become liquid. Now, this is different for every substance, but it's true that all substances have some sort of interactions between them that allow them to become liquid at a certain temperature or, in some cases, pressure. So the fact that real gases can actually become liquid means that there's some intermediate range where they're still gases, but they're kind of attracted to each other. And that violates this principle of the ideal gas law that says that they're non-interacting and causes the pressure to be different than we would expect with the ideal gas law. At some extreme pressures, it actually works the other way around. We can compress a gas so much that they start to repel each other because we're trying to push the atoms in the same space. They don't want to do that. So how do we describe real gases? Well, instead of using this ideal gas law, which is inadequate at these very high pressures and low volumes, we want to turn to these blue and purple equations and see what they are. The most widely used one is called the van der Waals equation of state. So rather than the ideal gas equation of state, we're turning to these other equations of state. So you can recognize some similarities here. So here we have P is equal to not nRT over V, but RT over Vm minus B. Now, this Vm is the molar volume, which is the volume divided by the number of moles. So this removes the N from these equations. We could put the equation back in if we wanted to. We would get P is equal to nRT over V minus NB, and then we'd have N squared A over B squared. So we could put the N back in. A lot of times we leave it out. So we had this equation where we have P equals now, instead of nRT over V, it's RT Vm minus B, and then minus A over Vm squared. Let's look at a different equation before we talk about what A and B are. The second most commonly used, the easiest one here, the Redlich-Kwong equation. Again, we can see it's kind of similar. We have this RT Vm minus B, but then we have this other term. Now we have a T squared dependence, and we also have this B over here as well. Now, what are A and B? A and B are gas-specific parameters that take into account deviations from the ideal gas law. So the A parameter measures the attractive strength of a gas. So how likely the gas molecules are actually to attract themselves to each other. And B measures the finite volume that a gas has. So gases aren't point masses, but they actually take up space. And so you can see if both of these parameters are zero, if there's no attractive strength between gas atoms and there's no volume of the gas atoms, we have the ideal gas law. So these are the assumptions that we have for the ideal gas in both of these cases. The A and B parameters serve the same point in both the van der Waals equation and the Redlich-Kwong equation. They are not the same. So the van der Waals gas, if we said try to find the van der Waals equation for like oxygen, it would have an A parameter and a B parameter. If we did that for Redlich-Kwong equation, they would be different parameters. And these parameters can be obtained from experiment, and we'll also see how they can kind of come out of these equations and considering the phase changes and so forth. Now, these equations themselves aren't as grounded in theory as the ideal gas law, and maybe as we would like. These come from fitting curves. So trying to fit these sorts of curves on this slide results in both of these equations. And you can see the van der Waals equation in purple does a little bit better, or I say much better than the ideal gas law, and then the Redlich-Kwong is a little bit better than that. There are a couple of other ones I will just mention here. So another equation of state is the Beatty-Bridgman equation of state. This uses 5 adjustable parameters rather than 2. So it can get a little bit more accurate, but then you have more fitting going on. Another one that's of particular interest is called the virial equation of state. This equation of state, rather than trying to just fit the data with things that work, uses a series expansion. And so we say that the pressure is equal to RT times 1 over the molar volume, ideal gas law. And then we add in other terms where we can keep dividing by this increasing magnitudes of the molar volume here. And this equation of state uses a series expansion to construct, B and C and so forth. So it's a little bit more grounded in theory. These can be pretty hard to actually try to come up with what these B and C functions are. So we're typically going to focus on the van der Waals equation of state. If we're working with a real gas equation of state, it's probably going to be the van der Waals. Now, what happens to a gas as we compress it? Or as we change the volume and pressure? We can look at this here and try to see what one of these gases would do. This is for carbon dioxide. And note that, again, we're under pretty extreme molar volumes, very small molar volumes. And so you can see that in this dashed line is the ideal gas law. And the ideal gas law doesn't quite cut it for this gas. This is at 334. It's pretty far off from what this should be. Now, you'll note something else kind of weird here is that these curves aren't really curves. So especially at low temperatures, so say 243, 258, 274, there are these weird horizontal lines here. What's happening at these horizontal lines? Well, in this case, the gas is doing what gases do under very high pressures and small molar volumes, and that is it's turning into a liquid. Why does the pressure stay the same? Well, consider what's going to happen as you compress a liquid. So if we have carbon dioxide, here we have carbon dioxide in a piston, and we can increase the pressure. As we increase the pressure, the volume of the gas will decrease, and we can see this here. What happens is as we increase the pressure and decrease the volume of the gas, at some point, it's more favorable for the gas to be a liquid than to keep being compressed as a gas. So once we hit this point, say point B here, and we're looking at this yellow curve, we're at a point where we're converting gas to liquid. Now, as we keep decreasing the volume, so pushing on it, we don't actually change the pressure, and what we change is actually the amount of gas in the gas phase. So the volume can get smaller and smaller and smaller and smaller and smaller as we convert gaseous carbon dioxide into liquid carbon dioxide without changing the pressure at all. And then once we get rid of all the gas, we hit the end of this line here, and then the pressure would increase massively as we tried to shrink the volume because liquids are relatively incompressible. It turns out that our van der Waals equation of state, nor any of our equations of state with only two parameters, are actually capable of recapitulating the curves that we saw before. Now, what happens to them? Let's look at this here. This is an example of a van der Waals gas. As we decrease the temperature, we would expect to see a curve like we saw on the slide. So let's see what happens if we decrease the temperature. As we go down, our curve starts to deviate from what kind of looks ideal, but at some point we get this weird, funky oscillation going on here. Now, you'll note that this is not what the data looks like, and that's for good reason. So what does this mean? Well, on the x-axis here, we have volume, and on the y-axis, we have pressure. So if we look in this region, what this region is suggesting is that as the volume gets smaller, the pressure gets smaller, and that is wholly unrealistic. Here we should have, like we see at high temperatures, the pressure always increases as the volume decreases. So what's going on in these funky regions? Essentially, our real gas law is breaking down. To generate the curves as shown on the slide, what happens is we take this oscillating region and we essentially just cut it in half. So we look at this region where it's half and half on each side, and then just draw a straight line. And that's how we get these curves generated that are on the slide. And that's called the Maxwell construction. So if we go all the way down to 258 degrees, this lowest temperature here, that is what this curve would look like. It would look something like this. And what we've done is taken this area and this area and essentially canceled them out. Another thing we can note is that there's one particular temperature, here it's given some more sig figs than others, 304.12 Kelvin, that doesn't seem to have this transition. It seems to go right from being a gas into a liquid with no transition in between. This is called the critical point. And you may have heard of this before. We'll look at this into more detail in the next chapter. The critical point is this very interesting point where the density of the liquid and the density of the gas become the same, and they can no longer be distinguished. You can note that if we look at this curve right here, there's a relationship between pressure and volume, namely that the derivative of the pressure with respect to volume right here is 0. We're at the maximum here. And we actually have an inflection point. Going back to calculus, at an inflection point, not only is the derivative equal to 0, but the second derivative is equal to 0. So the derivative of pressure with respect to volume is 0, and the second derivative of pressure with respect to volume is equal to 0. Now, why is that noteworthy? It turns out that we can use that to actually derive the A and B constants that are used to describe real gases using the van der Waals equation of state. So we can use this fact to come up with some theory for what these A and B constants should be. And we'll go ahead and go to the board and do that. So here we have the van der Waals equation of state along with its first and second derivative. Now remember, at the critical point, the first and second derivative of this are equal to 0. So this actually allows us to solve for what the critical temperature and volume are. So what we'll do is say that these are equal to 0 at the critical temperature and volume. So we'll put these C subscripts in on the temperatures and volume to remind us that we're specifically talking about the critical temperature and volume. So we can go ahead and solve these equations. For the first one, we will have 2A over the molar volume at the critical point cubed is equal to RTC over VMC minus B squared. And then for the second one, we'll have 6A over VMC to the fourth is equal to 2RTC over VMC minus B cubed. Now what we have here is essentially two equations and two unknowns. We can manipulate this to solve. The way I'm going to do it is actually by setting RTC equal to each other. It seems easiest to me to do that. So if we rearrange this in terms of RTC for the first equation, we'll get that RTC is equal to 2A times VMC minus B squared over VMC cubed. So now that we know what RTC is, we can actually substitute this guy in for RTC here, and that will eliminate the TC variable. So doing that gives us 6A over 4 over VMC to the fourth is equal to 2 over VMC minus B cubed, and then we'll put in for RTC, we'll put in 2A VMC minus B squared over VMC cubed. So now we can cancel some things out. We can cancel out this VMC minus B squared if we take away these cubed here. We can cancel out both A's. We can cancel out all VMCs on this side if we cancel out 3 of them on this side. And so if we do that, I'll go ahead and rewrite this as 6 over VMC is equal to 4 over VMC minus B. We can multiply both of these by their denominators to get rid of them. That's going to give us 6 VMC minus 6B is equal to 4 VMC. We can, again, rearrange this here, and that's going to give us then 2 VMC is equal to 6B, or VMC is equal to 3B. So B, remember, is one of our van der Waals parameters, and 3 times that B is equal to the molar volume at the critical point. Knowing this, we can go ahead and plug it back into our equation. So I'll take this VMC and I'll plug it in up there. So we know that TC is equal to 1 over R times 2A, and then we have VMC minus B. We know that it's 3B, so now we have 3B minus B squared over 3B cubed. So plugging that all in, we'll get 1 over R times 2A times 4B squared over 27B cubed, or 8A over 27RB. And here we have an equation for what T is. Taking both of these back into the original definition of pressure will allow us to solve for pressure. So we can say that pressure is equal to R, and now TC, so which is 8A over 27RB, over the molar volume minus B, which is 3B minus B. And then we have minus A over the molar volume squared, so 3B squared. And we can rearrange this to get the following. We'll get 8A over 27B over 2B minus A over 9B squared. Multiplying these by B squared to eliminate, we'll get that 4A over 27B squared minus 3A over 27B squared is equal to A over 27B squared as our definition for the critical temperature. So here we have that the critical molar volume is 3B, the critical molar temperature is 8A over 27RB, and the critical pressure is at A over 27B squared. What we can do with this is actually rearrange these to solve for what A and B are. So we can do some rearrangement here to determine that A is equal to 27R squared times the critical temperature squared over 64 times the critical pressure, and B is equal to R times the critical temperature over 8 times the critical pressure. And this is actually how these A and B parameters are calculated. Now, this is for the van der Waals equation of state. We could do a similar thing for the Redlich-Kwong equation of state to get the Redlich-Kwong A and B parameters. But this is where the A and B parameters come from experimentally. Another question we might have is how much error would we have if we use the ideal gas law to describe a gas rather than use its real gas law, or as close as we can get to a real gas law? One way we can do this is with the compression factor. The compression factor is the ratio between the actual molar volume Vm and what the molar volume would be if it was an ideal gas. And we can rearrange this into the following form of PVm over RT. If our molar volume is the same as the ideal molar volume, we would have PV over nRT, right? And that would be 1. So a Z factor, a compression factor of 1 indicates ideal gases, and different compression factors indicate different non-ideal gases. If the Z is greater than 1, that means the pressure is larger than we would expect it to be based on the ideal gas law, and the repulsive part of the potential is dominating. If it's less than 1, the attractive parts are dominating, and the pressure is less than we would expect it to be because the gas is closer together than we would expect it to be. We can see that depending on the temperature, we get some pretty different components here. So at low temperatures for this gas, the attractive potential dominates and causes the gas to be much more compressed than we would expect. At higher temperatures, that's not true, and the repulsive potential is always dominating, and the pressure is higher than we would expect. Now, there's a very interesting temperature, and that's shown here. Also note that the experimental data don't really match very well with the predictions. So in red, we have the Redlich-Kwong, and in purple, we have the van der Waals. They kind of do an okay job, but they mostly just predict the general shape of these things rather than the actual data themselves. But looking at this van der Waals equation, we can see something interesting. So this van der Waals equation at 400 Kelvin sits at 1 for a long time. Now, what does that mean? It means that there's a pretty high range of pressure at 400 Kelvin, or at least predicted at 400 Kelvin. You can see that the actual data don't quite bear that out to the different temperature. But there's a large range of data here for which the gas is approximately ideal. So at 400 Kelvin, we would predict that this gas would have a compression factor of 1, that is, be ideal for roughly looks like 70 or so bar. That's a lot of pressure. So here we have another example of this, and we can see that at high temperatures, at 525, our repulsion is dominating. As we drop this temperature, we can see it start to approach this limit. And here at about 400, we are, just like we saw on the slides, at 0, right, or at 1 essentially, at no change for a great number of pressures here. And if we keep increasing it down, we do see that dip like we saw before, and we can get some pretty significant deviations. So what is going on here, and how do we describe this? Well, we can describe this by looking for the limit as the pressure approaches 0 of the slope of this curve. So the slope of this curve, if it's 0, that means it's unchanging. At a pressure of 0, the volume is infinite and all gases would be ideal. So they all will approach 1 as the pressure goes to 0. But if we want that slope to be 0, we can set this limit of the derivative of the Z factor with respect to pressure at constant temperature. We can set that, we can take the limit as the pressure goes to 0 and set that equal to 0. And what we end up finding is some temperature called the Boyle temperature that describes this phenomenon. We'll go through that in the slides as well. What we're trying to do here is evaluate the limit as the pressure goes to 0 of the derivative of our compression factor Z with respect to pressure. We can also say that this is equal to the limit as the molar volume goes to infinity, since that is what happens as the pressure goes to 0. Now, this derivative is actually relatively cumbersome to take. We know that Z is equal to P times the molar volume over RT. How do we take this, the derivative of this with respect to pressure? What we're actually going to do is the following. We're going to recognize that the derivative of the compression factor with respect to pressure is equal to the derivative of the compression factor with respect to molar volume, and then multiplied by the derivative of the molar volume with respect to the pressure. And then we're going to use our laws of how we can manipulate these things to say that this is equal to the derivative of the compression factor with respect to molar volume, and then divided by 1 over this guy here. So divided by the derivative of pressure with respect to molar volume at constant temperature. So these are things we can evaluate. We can plug in the van der Waals equation of state for the pressure and take the derivative of that times Vm over RT with respect to molar volume. And then we can just take the derivative of the van der Waals equation of state with respect to molar volume. Now this is kind of nasty. So what we end up getting then is we try to take the derivative with respect to molar volume of the following. And we're not actually going to go about doing it again. It's not too hard, but it's kind of gross. So Vm over Vm minus B minus A over Vm RT. So what we've done is simply multiply the van der Waals equation of state by Vm over RT. And then we're going to divide this by the derivative with respect to the molar volume of the normal van der Waals equation of state. That is RT over Vm minus B minus A over Vm squared. And so in doing this, we end up with the following. So taking these derivatives, what do we get? We get, from the first term, we get minus B over Vm minus B squared plus A over RT Vm squared. And then we want to divide this by negative RT over Vm minus B squared plus 2A over Vm cubed. So from here, what we're going to do is actually apply this limit here. We're going to take the limit as the molar volume goes to infinity. So how do we do that? So as the molar volume goes to infinity, what happens to this equation? Well, in this first term, infinity, if molar volume is infinity, infinity minus B is still infinity. So what we can do then is boil down this term here to simply minus B over Vm squared. So an infinite number minus a finite number is still that infinite number. And we leave this one alone because there's no terms here, there's no addition and subtraction to get rid of. In this second part, we'll do the same thing. So we'll say that this is equal now to minus RT over Vm squared. And we're actually going to just leave it at that. Now, how can we do that? Well, note that in this denominator, we have Vm squared, while in this denominator, we have Vm cubed. If Vm is a very large number, the cubed term is going to be much, much smaller than the squared term. So we can just ignore it in this infinite limit. Then that actually gives us something that we could solve pretty easily. So we'll simply take minus B over Vm squared and then plus A over RT Vm squared. And now we're multiplying by Vm over RT. We can do some cancellations if we want, and we end up with this being 1 over RT times B minus A over RT. Now remember, the point of this is that when the molar volume is going to infinity, as the pressure is going to 0, the limit of this should be approaching 0. Again, this being the slope, how the rate of change of the compression factor with respect to pressure. If that's 0, then we have an ideal gas. So if we set this equal to 0, we can rearrange this and find that B is equal to A over RT, and then we can say that T is equal to A over RB. And we'll put a B here for the boil temperature. This is the temperature at which we predict the compression factor, or the compression factor to be 1, and the slope of the compression factor to be 0 for a large range of pressures. As we saw on the board, a real gas acts ideally at its boil temperature. Again, we can note that this van der Waals equation doesn't predict the boil temperature super well. It does an okay job. But there is a real boil temperature, even if it's not able to be very accurately predicted by this equation of state. And this is a temperature at which gases behave ideally for a large variety of pressures. Here we can see some data where the oxygen here, the experimental data is at its boil temperature, and you can see it has a compression factor of 1 for up to and maybe even a little bit beyond 100 bar. The equation doesn't quite predict it, but you can see it's very different. Different gases like hydrogen, so hydrogen at 400 Kelvin is always repulsive. Ethene is pretty attracted at that temperature still. So every gas is different and has its own boil temperature. Now, something that we can note, and we noted it before, is that even though gases have these different equations of state based on these A and B parameters, every gas is kind of similar at its critical point. So if we have a gas and it's a critical point, we have this supercritical fluid, and it doesn't really matter what the gas is anymore. We kind of liquefied this gas without actually turning it into a liquid, or we gasified the liquid state of matter here. So the law of corresponding states states that different gases have the same equation of state if each gas is described by the dimensionless reduced variables based on the critical point. And what do I mean? We'll go ahead and see that in the slides. What we'll do to formulate the law of corresponding states is to take the variables of pressure, temperature, and molar volume and turn them into reduced variables. So what we're saying is that the actual pressure is equal to the reduced pressure times the pressure at the critical point. And the same is going to be true for the temperature, and the same again will be true for the molar volume. Now, when we're doing this, what we're going to end up with is an equation that depends only on the reduced variables. And then we'll get the critical points and substitute in what A and B are to eliminate them there. So what's going to happen? Let's go ahead and take a look. So we'll plug in all of these variables for P, T, and V, and we'll get that PR, PC is equal to R, TR, TC over VMR, VMC minus B, and then minus A over VMR squared, VMC squared. What we'll do now is plug in for the critical temperature, pressure, and volume their A and B dependence. So that is going to get us on the left-hand side, A over 27B squared times PR is equal to 8A over 27RB times RTR over 3B VMR minus B, and then minus A over 9B squared VMR squared. Here we can simplify a little bit, so we'll cancel out these R's, and then I'm going to try to rearrange this equation so we have A over 27B on every term. So we already have A over 27B here on the left-hand side. Now on the right-hand side, we can simply pull out a B. So this will give us 8A over 27B, and what's we're left over with then is TR 3 VMR minus 1. And then on this last term, we simply have to multiply by 3. So we'll have 3 over VMR squared, and then we'll have our A over 27B squared term here. And so when we have arranged in this way, we can cancel out the A over 27B from each term. And this then gives us PR is equal to 8TR over 3 VMR minus 1 minus 3 over VMR squared. And this is our law of corresponding states. This relates the reduced pressure, temperature, and volume of any gas based on its critical point alone without resorting explicitly to any individual parameter. Here we can see the conglomeration of a whole bunch of different gases. You can see that there are very many different types of gases. We have nitrogen, we have isopentane, right? We have a whole bunch of different types of gases that are very different, going from small to large. And yet they all actually, remarkably, fit on this curve pretty well when we've reduced them to their reduced variables, looking at the reduced pressure and temperature. So we actually have an equation of state that does a pretty good job of predicting what these gases might do as a function of their critical point. Now, we've kind of cheated a little bit here in that we're trying to get an equation of state that doesn't depend on any parameters specific to the substance. And we kind of don't, because we can use this equation of state for any gas. However, they're very different because the reduced pressure, volume, and temperature is different depending on the substance that we're investigating. So we can look at hydrogen and bromine, molecular hydrogen, molecular bromine, at the same reduced pressure, temperature, and volume, and see how different they all are. So hydrogen would be at 13 bar, 64 mils for its molar volume at about 33 Kelvin, whereas bromine under the same conditions would be 103 bar, 127 mils for the molar volume and 588 Kelvin. So we do kind of have these substance-specific parameters in there. They're just kind of hidden away. So the law of corresponding states is pretty good, and it shows us that we can relate gases. We can kind of get to what we want, which is an equation of state that describes real gases without resorting to the parameters, even though we kind of are resorting to the parameters. Lastly, I want to briefly mention the term fugacity. The fugacity is simply the actual pressure that an ideal gas exerts. Under conditions where the attractive part of the potential dominates, the fugacity would be less than the pressure, just like our Z would be less than 1. Under conditions where the repulsive part dominates, the fugacity is greater than the pressure. The fugacity differs from the pressure by multiplying it by this constant gamma, where gamma is a function of temperature and pressure. I'm not going to go too much into the details here. Now, why do we mention fugacity? If you are a chemist and you're actually trying to do maybe some extreme gas phase reactions, a common example would be to synthesize ammonia for use in fertilizer. It's not good enough to talk about the pressure of the nitrogen and the hydrogen and the ammonia. You actually have to consider their fugacity, which is simply the real pressure multiplied by this correction term. And then we can do the same things we've done before. So we can calculate an equilibrium constant based on fugacity rather than based on the partial pressure. And that's simply a breakdown like we've seen before. So the Kf, the equilibrium constant based on the fugacity, would be the fugacities of ammonia and the fugacity of nitrogen and hydrogen, which is this gamma coefficient times the pressure. So it's based on the equilibrium constant, based on pressures as we would calculate, but based on the fugacity coefficients, we'd have a different answer. And this can actually get some pretty different answers. So under the normal conditions used to synthesize ammonia, the fugacity equilibrium constant is only about 80% of the pressure-based one. So you're going to get less ammonia than we think we should. And this is important to know when designing apparatus to do this large-scale synthesis. All right, to conclude, most gases are approximately ideal under normal conditions, standard temperature and pressure. However, they are not perfectly ideal, and that's because they have attractive potentials and can actually form liquids. We'll look more into that in the next section. We can come up with real gas laws, but these real gas laws are based upon experimental observations, and so they often fall short. One way we can remove the experimental parameters that are necessary to set up these equations is by comparing gases based at their critical points, and we can formulate the law of corresponding states. And then to get really accurate equilibrium constants, which is necessary in some branches of chemistry, we have to consider fugacity, which is simply a modification of the partial pressure. And so with that, I look forward to talking with you guys about real gases in class, and then we'll move on to phase changes in the next lecture.